Well, thanks for the introduction and for your patience. My talk is going to be a little different. It's not going to be about YARA rules per se, but more about what those rules end up as. A couple of years ago, or since a couple of years ago, I've been involved in developing tools that were used in incident response contexts and that used YARA. And at least one of those tools was done for basically a service provider, and we considered our rule sets that were based on our own research. In part, we considered those as trade secrets. At least we considered to be a tactical advantage to be able to hide them from attackers, and hope we were successful in that. And I have always been wondering, well, what we did was we didn't ship the tool together with YARA rule sets in plain text, but in a compiled form. And I've been wondering since then how easy it might be to actually reconstruct the individual rules. Looking with strings, with the strings utility at the compiled rule set, showed us that it was pretty easy to see the actual pattern strings, but I've been wondering about the condition syntax, what it ends up as. So we're going to have to we're going to take a look at that and do some deep dive into the YARA compiler and come up with some possible improvements to YARA. And I have to warn you, there might be some C and assembly included. So what actually happens when you compile a rule set? In the top, I've taken an example from the signature base rule set from Florian Roth. And this is a command line that is used, or part of a command line that is used to compile the whole rule set into one file. And within the YARA compiler, what actually gets called a lot is this YARA compile add file function. And behind the scenes, there is a single parts compiler that's driven from a proper grammar, and it builds basically a large data structure. The strings and regular expressions, they go into a variant of the aochoretic automaton. And then there are rule names, meta information, as we've seen before. They get pretty much stored as is in the file, and they're well visible in the compiled rule set. And then there are the conditions. Those are compiled. All the conditions are taken and they are compiled into a single bytecode program, and that's what we are interested for the purpose of this talk. Everything is that's allocated in main memory of the YARA compiler and later in the YARA scanner. This is allocated in so-called arenas. It's a custom memory allocator that supports pointer relocation for data structures, and it makes it really easy to load and save compiled rules from or to disk. And all that's needed for this to work is that it has to know for every data structure where this data structure contains other pointers, and the whole thing has to be self-contained. When we do scanning, when we load this compiled rule set and maybe pass it some external variables and scan a file with it, the YARA rules scan file function is called. And well, this executes this multi-pattern matcher that has been built up for which the automaton has been built up in the compiling stage. And when that is done, this bytecode program is interpreted. And without the bytecode program, nothing would be output. No rules would be matching, because the bytecode program collects all the matches and well, evaluates a lot of expressions for that, and that's what we're going to be looking at. Well, if you read a file, it's pretty easy, but you can also scan process memory, and there things get a little more complicated, because process memory on most operating systems is not one big blob of memory, but it's contained within regions, and for this an iterator implementation is used. So the file or process memory is being read multiple times, once for pattern matching, and when the rules bytecode program, the conditions bytecode program is run, it may be read again. And if you are not smart about how you write your conditions, this might be slowing down process memory scanning. And there's one more note: you can build upon the iterator. You could build something that supports streaming operations, but you'd have to store the stream to support this kind of operation that I just described. So we have this bytecode engine that's being run. It's a stack-based machine, a stack-based virtual machine, and with a pretty similar opcode format, just one byte opcode, and the operands. There might be one direct operand, and everything, pretty much everything, happens on the stack. The stack holds operands and results for basic operations, such as adding numbers or subtracting numbers or what have you, and that is readable and writable, of course. There's some scratch memory that the bytecode program can use. That's pretty small, and I believe that it's only being used when the compiler emits loops. And then there's the arena, the bit of compiled YARA rules that I talked about above, and we can only read from that. And then there's the input file, which also can only be read, and which is backed by this iterator. The bytecode engine is implemented as a giant switch statement. We have some pretty normal, I would say, instruction set. We can do arithmetic and logical operations for integer and float values, and they're all 64-bit. We can do string compares. What is actually being used there is, or passed around there, as we will see shortly, is pointers, and well, the string compare is actually backed by a C string compare function. Then we have data conversions. The integer can be converted to float, or string can be converted to Boolean, but not the other way around. I think that it was just those were just implemented as they were needed. And then there are conditional jumps, and the targets of those conditional jumps are all relative addresses, so all within the same program. And as we'll see, they will stay within the same rule set. But the main point here is that our code is position independent. Of course, the program, this virtual processor, this virtual machine, has to access the stack and the scratch memory. And we, of course, have to be looking up if individual strings that that are together defined together with a condition have matched or not, and do all sorts of evaluation on that. We can count and group string matches and have these familiar any of a specific kind of string or all of the matches. This gets compiled to a different instruction, so as we will see. Then there's module support, like the famous PE module. It is imported. There's an import statement that translates directly to an opcode, and this triggers the initialization of the module. The YARA compiler will emit this only once. So if you have multiple import statements for the same module, that won't matter. This import opcode will only be created once. We have an iterator that's used for loops. Of course, we can access the input file directly, as we have seen with the famous lookup for MZ to check if there if the file at hand might be in a PE executable. And then there are external variables that are provided by modules, and we can even call into functions that are defined within the modules. The file size operator, and we can there's a function, there's an opcode that marks a specific rule or checks results from different rules, and finally there's a halt instruction. The halt instruction is always emitted. It does pretty much what it says. I've written a small disassembler for this bytecode machine language, and what you're seeing here is output from this disassembler. And we will be going through some examples, some simple examples, and work our way up from there. For the first rule, that's just condition true. It says that the rule structure is initialized, and there's the next marker next to it means that if this rule has been disabled through the YARA API, its code will just be skipped. In this case, we'll be pushing a truthy value, just the number 1 to the stack, and the match rule operation that comes below that will take this value from the stack and record this as a match for rule number 0, which is called T in this case. Same thing, only we're pushing a falsy value 0 to the stack for the rule below. We can look at string matches, as I said, and this looks like the code below. Pushes a number of strings, the minimum number of strings that have to be matched onto the stack, an undefined value as the end of string list marker, and then offsets to two string objects that have been created by the compiler. The off operation unrolls the stack, looks at it, at its operands, and determines if at least one string in this case has matched, and pushes that to the stack where it's picked up by the match rule operator, and that's it. can we can match all strings in a given list in a similar fashion. The only difference here is that there's no minimum number of strings being pushed to the stack here, but also an undefined value, and it's in other ways it's no different. One thing to note is that the addresses that are being pushed to the stack, they in this case are actual addresses as they are presented in memory. So wherever the YARA library has loaded its compiled rule set, there the strings those addresses are being used for the for the push operations here. So those are pointers to actual memory, and this is the result of the relocation mechanism I described before. We can use modules, as I said. The tests module is being built with YARA for basically for test purposes, and this is an example for lookup within more complex dictionaries or more complicated data structures. The PE module has similar data structures that it defines, and those are all referenced by their by strings. And the strings are pushed to the stack as before. But one thing to note here is that this test string has actually been emitted into the YARA rule set 3 times, and constants has been emitted 2 times. You can see that from the different pointers that are being pushed to the stack. So the strings are pushed to the stack. Then a lookup operation is performed, and in the end, there are, in this case, the numbers integers 1 and integers 2 on the stack, and they are compared, and the rule will match actually. A similar thing can be done with external variables. We can string compare external variables to strings to a given string, or maybe we can compare those variables to each other. It doesn't really matter. But again, offsets are pointers are being pushed to the stack, and the string compare operation takes them and pushes the true or false value onto the stack, where it's then eventually evaluated by the match rule operation. One thing to note here is the J-true at offset 1D. That's actually a short circuit operation. So if file name is actually Explorer.exe, then it goes straight to the match rule operation. Putting it all together, or putting multiple rules together that we haven't done that before. Since the code is position independent, it's all you can all concatenate it, and that's what the YARA compiler does. And so everything is evaluated in order until the halt instruction. I've looked at the signature-based rule set that's being maintained by Florian Roth. It's the combined YARA rule set currently contains just under 3,500 individual rules, over 17,000 strings patterns, over 60,000 instructions, which evaluate to over 429,000 bytes. So that's quite a lot of bytecode there, and the file size, all in all, is about 7.5 megabytes. I didn't list the original size, but well, as we've seen before, strings are being emitted and not checked for duplicate strings. So there are optimization possibilities in the YARA rule compiler, and I think that would be a great way to save on space. Florian just tweeted a few days ago that he had seen big improvements with YARA 4.0. But I think there might be even some more some more opportunities for optimization. If you don't actually use your meta information and are only interested in patterns, and file size for the compiled rule set is of concern to you, you might want to strip those. So maybe the YARA compiler should offer an option to just skip those, or maybe skip the pattern names also. And as we've seen in the examples, the instructions are quite sparse. There's not really a need to be pushing or to be encoding 64 bits for every small value that you push onto the stack. So there might be some optimization opportunity there too. So what can we do with this? Really, if we can disassemble, maybe you can assemble some programs. This is not going to be useful for actual rules, but I decided to look at this and see where this gets us. I'm running a little short on time, so I'll skip over the slide. The main thing is that we cannot really do any proper output. Input is easy, you just use the input file, but output is something that's not built into YARA as accessible feature from the rule set bytecode. So I implemented a little putcar function to overcome that. The YARA output, this will just output some characters, and that's it. Have no real value otherwise. This is a YARA bytecode program that basically does the same thing, but this is not what the compiler actually emits. So I've started writing an assembler, and this is something where we can write our own programs. Well, we might be able to port some C code. Just kidding. This is a Mandelbrot set program that's really obfuscated, but I've been able to port this to YARA bytecode. Oops. And it made no sense to put this on the slides really, because it's too long. This is what it's ended up as. Because we have no strings, I have encoded the characters that are output into 64-bit numbers and do some shift operations on them and call that podcarg function. And need to tell YARA that it's actually going to be reading compiled rule set, and this is what it will output, all calculated by the bytecode engine. So this concludes my talk. There is an acknowledgement slides, but I think we've really run out of time. And yeah, my contact info. I will be releasing the disassembler and the assembler after I have cleaned up the tools. And well, thank you very much for your attention. And if there's time for questions, I'll be happy to do my best to answer them. Thank you very much.
Thank you, Hilko. I appreciate it. I think looking at the time, I don't think we have time for questions, but if we have any questions, we can supply you with the questions from the Q&A, and we can answer them offline later. And thank you very much. Next up, we have Joe John. Yes, absolutely. Thank you very much.